Hello grade 11 AP Maths. This is my first interaction with you while you are in quarantine. So am I. So I hope you enjoy now. These lessons are going to be recorded. These lessons are going to stay in Google Classroom. So this is your time with me, KRM one-on-one. Quarantine lesson, we're going to touch Radian Measure again. I'm going to do a background check on what we learned about trigonometry. Some of you may have missed it because of major production. So I'm going to do that first, and after that we're going to move on to Radian Measure, which is the main topic. Remember, this is the beginning of calculus, and from here we're going to continue. So I hope you enjoy the first quarantine lesson on calculus. It's going to be amazing. As a background, I'm going to start with all the trigonometry first, starting from the very basic of the trigonometric of a Cartesian plane. So again, remember, this is basically a revision from the trigonometry of grade 10. The only thing that might be new to you at this point in time is that we're talking about reciprocal functions, but I'm sure your teachers in grade 10 would have also touched that. This is just core mathematics. I don't think that there's anything new here. I think that the only relationship that I've missed in this whole thing is the Pythagorean relationship. Remember that although we're talking in a Cartesian plane, the distance from the center to the point P, which is your square radius, is equals to the sum of x squared plus y squared, and that's your Pythagorean relation. From there, we moved on to formulas of reduction. What are formulas of reduction? In basics, formulas of reduction are formulas that allow us to convert any angle from any of the other three quadrants, from the second to the fourth quadrant, into an equivalent angle in the first quadrant. And we did this test in class. I asked you to calculate the sine of, for example, 45, 135, 225, 315, and you found that those angles had exactly the same value, obviously with different signs, simply because remember that the functions have different signs in different quadrants. In the first quadrant, all functions are positive. In the second one, only the sine is positive. In the third one is only the tan, and in the fourth one is only the cos. And obviously they are reciprocal functions as well, which are the cosec, the sec, and the cot. In the second quadrant, the formula of reduction is 180 minus theta. In the third one is 180 plus theta. In the fourth is 360 minus theta. Remember that the sine and the cosec are positive in the same quadrant, in other words, in the first and the second quadrant. The cos and the sec, which are the reciprocal of the other, are also positive in the same quadrants, in the first and the fourth quadrant. And the tan and the cot, which are the reciprocal of the other, are positive in the first and in the third quadrant. So basically this is a recap of what we did in terms of formulas of reduction. Moving on, we move to co-ratios. Okay, remember the co-ratios are ratios of complementary angles, in other words, angles which add up to 90 degrees in the first quadrant. So if two angles are up to 90 degrees, basically you can say that the sine of the one is equals to the cos of the other, the tan of the one equals the cot of the other, and the sec of the one is equals to the cosec of the other one. So that's basically your co-ratios. This applies basically to all trigonometric functions, and sometimes it's actually used for me to be able to take a function and convert it to something else, so that I have for the order in terms of simplifying the function. So it will be advisable for me sometimes to convert a cosec into 1 over sine, so that I can then simplify, because the nature of the question that I'm answering calls for that. The fourth element that I want to recap with you are the identities. In core mathematics, there are a group of identities. They start in grade 11 with the main Pythagorean identity, which is this one, and I did demonstrate it in class, that the sine square of theta plus the cos square of theta equals to 1, theta being an angle, okay, and in this case it doesn't really have to be an acute angle, it can be any angle, for as long as theta is the same angle, sine square plus cos square will always be 1. There's a couple of other ones, and that is the 1 plus the tan square is equals to the sec square, 1 plus the cot square is equals to the cosec square. If you were not in class when we did these identities, I will ask you to please call on one of your peers and get the questions or the proof of these identities. They are actually very simple. Coming back to where we started, if you use your trigonometric ratios of the standard Cartesian plane, you'll be able to prove the identities very, very simple. Okay, so moving on now, and then what we did was we moved on to the trigonometric rules for a non-right angle triangle. Remember that these are rules that apply to any triangle, and I did mention in class, they also applies to a right angle triangle, But because in the right angle triangle I've got the trigonometric ratios that are well defined, I don't really need to use these rules. What do these rules allow me to do? By all of them, the area rule, well, not the area rule, but the sine rule and the cosine rule, they both allow me to solve a triangle. What solving a triangle means is being able to find the size of all the interior angles as well as the length of all the sides in the triangle. The area rule allows me to calculate the area of a triangle without having to know the height. So all I need to know is two sides and the angle between those two sides, and that will allow me to solve or to find the area of a triangle. This also can be proven using last year's core mathematics trigonometry, but I'm not going to go into the proving. We're just going to take this as a proven fact. So I'm going to start with the area rule, and as I said, the area rule is the area that applies to calculating the area of a triangle for as long as I know two sides and the angle between them. So I could write it as a half of AB times the sine C, or I could write it as a half of BC times the sine A, or it could be a half of AC times the sine B. So for as long as I know two sides and the angle between, I can always find the area of a triangle. The sine rule is basically a ratio which establishes and allows me to also solve a triangle. Remember, when you equate two ratios, you have a proportion. So using the rules of proportion, I will be able to find any given element in a triangle for as long as I know another three that are in certain order. What is the order here? The specific order is that two of those three elements must be an angle and the side opposite to that angle. So if you know the angle A and the side A, or the angle B and the sine B, and the side B, sorry, or the angle C and the side C, you can always use this rule plus any other element. So in this case, I could say if I knew angle A and side A, and either angle B or side B, I could use the proportion in order to find the other one that I'm missing. There are two ways of writing this. As you can see, they are not really different. The only difference is the fractions are upside down. But because this is a ratio, remember that for as long as you keep the same order, okay, you will always obtain the same radio. What is critical for me to know here is that I need to know an angle and its opposite side plus another piece of information to be able to solve a triangle using the sine rule. Okay? Right. The cosine rule, which is now the other rule, and the reason why I'm saying is the other rule is because I can use the cosine rule whenever I cannot use the sine rule. So if it's not possible to use the sine rule, in other words, I don't know a side and an angle opposite to it and another piece of information for me to use the sine rule, then I go the cosine rule. What are the two basic reasons for me to use the cosine rule? The cosine rule allows me to find the side of a triangle, and again I'm talking about any triangle, and I'm going to recreate the triangle that I drew on the board. So this triangle A, B, C, side A, side B, side C. So if I know two sides and the angle between them, and I know that this sounds a little bit familiar because these were the conditions that I had to have in order to find to use the area rule, okay? But also I could solve the triangle by using the same conditions that I need for the area rule in order to use the cosine rule. So if I know two sides and the angle between them, I could use the cosine rule. In this case, if I needed to find side A, I would say B squared plus C squared minus 2 times B times C times the cos of A, or vice versa. If I needed to find B, I will go and use the same. So B squared will be equals to A squared plus C squared minus 2 times A times C times the cos of B, which is the angle between A and C. Needed to find C, that would be A squared plus B squared minus 2 times A times B times the cos of angle C. In the same way, I could also use the cosine rule if I knew the three sides of a triangle and I needed to find one of the angles. So I could find any one of these angles provided that I know the three sides of a triangle using a variation of the cosine rule. This is not a new formula. You can actually obtain these three formulas if you were to make cos A, cos B and cos C respectively the subject of the formula in this equations, and that will just come up with this. So the only difference is that I will use this formula if I knew two sides and the angle between them and I needed to find the third side. I will use these formulas if I knew all three sides and I would need to find the size of an angle. Okay, so up until here we have all the background information that we needed from the lesson that we did just before we had to go on to quarantine. So the next up, I'm going to start then with the radian measure. I did touch on radian measure just getting to the end of the lesson on that day, but I didn't have the time to actually explain it in detail. That's coming up. So up until now, we've been accustomed to use degrees when it comes to measuring angles in trigonometry. The world still uses angles when they do measure, but in higher mathematics they tend to use radian measure because I think it's a more accurate way of using mathematics, and in again complex mathematics, calculus, etc. Always the angles are used, or angles are calculated using radian measure. So I'm going to explain throughout the next couple of minutes. I'm going to show you how do we convert between radian and degrees, and also what is a radian measure, how do we get to find what the measure of 1 radian is, okay, and how do we use it to determine the length of an arc and also the area of a sector in a circle. So let's start first by defining radian. So basically the definition goes that 1 radian is the measure of the central angle whose arc length is the same as the radius of a circle. So in a weird kind of way we can say the radian is actually the measure of the angle which will give me a triangular, equilateral sector, if you want to put it that way. We cannot say the word equilateral simply because one of the three is not a straight line, it's just a curve, and that is the arc, but just get the idea. Now if you think about it, a lot of people will say, well, so how do we get a radian measure? So what is equivalent to a radian measure? Would that be 60 degrees? No, it's not 60 degrees simply because remember that this is not straight. If that was straight, this angle is going to be a little higher. So I could say that a radian, okay, is slightly less than 60 degrees. Okay, I will find out exactly what the measure of 1 radian is. I think I will have to be able to find it, and I will tell you. You can also calculate it by simply dividing 180 by 3, or by pi, by the number pi in your calculator. So if you do that, you will find the value of 1 radian. Okay, and you will find obviously that is slightly less than 60 degrees, simply because, and going back here, if that was to be a straight line, obviously that angle is going to be a little larger. So as it is now, that angle will be under 60 degrees. If that was a straight line, then that angle will be 60 degrees because this will be an equilateral triangle. I hope you get the idea of what I'm talking about when I mention a radian. Now, how do we determine the relationship between radians and degrees? Okay, so what I'm going to do here is I'm going to say, so the measure of an angle ABC, and this is the measure of an angle ABC in radians, is to 360 degrees. So I'm establishing the ratio between a radian and 360 degrees as the length of the arc, okay, the length of the arc is to the circumference of the circle. Okay, and I missed an F here. Apologies for that. It's to the circumference of a circle. So what I'm going to do now to actually come out with some sort of a formula, I'm going to then multiply both sides by 360 degrees. I will be able to eliminate the 360 on this side. Simplified here, remember the arc is an arc of r, length r, okay, and the circumference of a circle, the total circumference of a circle using geometry or the formula is 2 pi r. I'm sure that you're all familiar with that. When I do then the multiplication of 360 on both sides of my proportion, I can then simplify the 360 degrees here, simplify the 360 with a 2, the r with the r, and I end up that 1 radian is equivalent to 180 degrees divided by pi. Pi being obviously that famous 3,142 number, irrational number, okay? Remember that in grade 5 or grade 6 in high school, a lot of your teachers said to you, use pi to be 22/7. And I think that we've had this conversation before. What is the difference between this pi and that pi? Is that this pi is rational, whereas the pi that we have to use here is irrational. For interest's sake, I will tell you that this pi never has to convert it because the calculations are not really going to have anything to do with the 22/7. So you can use the pi in your calculator. There's a pi in your server calculator, and you're welcome to use it anytime you need to use it for your radian measure. Okay, so based on that, I can then conclude that pi radian, so an angle of pi radian is equivalent to 180 degrees, and therefore a 2 pi radian angle is equivalent to 360 degrees. I'm going to now show you a couple of conversions of angles between radian and degrees. So here is my first example. I've got 3 angles, and I want to convert those 3 angles from degrees, okay, 60 degrees, 135 degrees, 206 degrees into radian measure. So how will I convert from degrees to radian? Well, simply I will do is I will multiply by pi over 180 degrees. Remember that 1 radian is 180 over pi, so 1 degree will be pi over 180. It's a reciprocal of this ratio. So 60 degrees into radian will be 60 times pi over 180, and that will turn out to be pi over 3. 135 degrees into radian, I will then multiply by 135 times pi over 180. Okay, and then I can just go into simplified. So let's see if I can simplify by 5. If I simplify by 5 here, so that's going to give me 27. Am I right? 27, that will give me 135. Okay, and if I divide by 5 here, that's going to give me 36. Okay, so I can say 27 and 36, they can still be simplified by 3. Yes? 3, so if I simplify 27 by 3, that's 9. If I simplify 36 by 3, that's 4. So I can then conclude that 135 degrees is equivalent to 9 pi over 4. Okay? And on the other side, we have that 206. Again, the same thing. I'm going to do the conversion. I will say 206 times pi over 180 degrees, and then do the conversion. And so for the interest sake of this exercise, I'm just going to leave it as 206 pi over 180. Okay, and that basically you will be able to simplify it. I think if I look at face value here, I can simplify it by 2 first of all. So I can say divided by 2, that would be 103 pi over 90. Okay, and I don't think that I can go any further. They're not divisible by 3, they're not divisible by 5, they're not divisible by 7. So for the sake of this exercise, I'm just going to leave it that, and that's the equivalent to 206 degrees. Okay, so some more examples coming up. So I'm going to start. Okay, we're still converting from degrees to radian. So you saw the example of the 60 degrees. I'm going to do now the example of a 45 degrees. So converting 45 degrees to radian, I would just multiply 45 by pi over 180 equals to pi over 4 when you simplify. If I try to change 270 degrees into radian, again I multiply by pi over 180, do my simplification by 90 degrees in both cases, and that means that 270 degrees is 70 degrees equivalent to 3 pi over 2. Okay, now to convert the other way around from radian to degrees, again as I said to you, so 1 radian is equivalent to how much? Is equivalent to 180 over pi degrees. So you want to convert 3 pi over 4 into degrees, again multiply by 180 over pi, simplify here, and that will give you 135 degrees. 7 pi over 9, okay, equals 2, again multiply by 180 over pi, simplified, and that comes with 140. In essence, what you need to know is this: if you are going to convert from radian to degree, you go and multiply by 180 over pi, okay, and that is what we've been doing here, okay. Whereas if you're going to convert from degree onto radian, then you multiply by pi over 180, and that is going to then give you the angle in radian. Okay, angles in radian, in some cases when the angles are small, you will be able to, or they will give you the value of the actual ratio. So they will not say 25 pi over 5, there was 25 pi over 7, just to put it in a proper fraction way. They will say 2,3 radians, okay, and that is the equivalent. So you can use the 2,3 radian just exactly as it is in your calculations. Okay, so how do we do the conversions using calculators and also without using a calculator in trigonometry? That's coming up. Hang on. And we're going to start now first with the use of a calculator, how we can use a calculator in order to solve problems involving radian measure. So with the calculator, using the calculator, let's say I want to determine, or I want to find the equivalent to 0.46 radian. 0.46 radian, and I want to convert that into radian into degree. Okay, again, how do I do that? Remember, if I go back to the previous screen, okay, I had that to convert from radian to degree, I multiply by 180 over pi. So that's what I'm going to do here. In your calculator, it will look like this. So we're just going to say, so started to 0.46, 0.46, okay, times, and I just use the fraction. You can use the fraction function in your calculator, and you say, well, it's 0.46 times 180 over pi, so 180 degrees over, and remember that you have a pi in your calculator at the bottom here. Okay, so you have a pi here, so I'll press shift and the back here, that will give you the number pi. In my calculator, press equal, and that will convert it. So 0.46 radian. Why has it got a minus? Oh, my apologies, I did multiply by a minus here instead of 180, so my apologies, the number is, let me just redo it. Okay, so let's go back and we say 0.46 times, and we say fraction, so we press a fraction, 180 over second function pi equals, and that is equals to 26.36. So you multiply 0.46 by 180 over pi, and that is equals to 26.36 degrees. And that's a conversion from radian to degrees using your calculator. Okay, degrees to radian, similar thing. So I'm going to go and say, so I need to determine then what is the, or let's convert, let's say 75 degrees to radian. Again, remember when you're multiplying, when you're converting from degrees to radian, what do we do? Going back to our previous slide, degrees to radian, you would multiply by pi over 180. So I take 75, multiply by pi over 180, okay, in your calculator. So it's 75 times pi over 180, so second function pi over 180 degrees, press equal, and that's going to give me that 75 is equals to 5 pi over 12. And that's basically what you need to know in terms of conversion. It is important you know how to convert, because sometimes, and I know the mindset, I mean, that I still, when I was at school, everything was in radians, but when I moved to South Africa, or to teach in Africa, everything became degrees, and I started working with degrees. And even today, I always convert from degrees to radian in order to think. So this will be not new for me, but in your case, because your mindset always been taught in degrees, you will now have to change all the time from degrees to radians in order to be able to do the conversion and use spatial angles. Okay, so I'm going to take you into how can we simplify an expression without the use of a calculator and using angles in radian. Now, again, I'm going to show you from the perspective that I think that you've always been taught in degrees, and I'm going to make some annotations here for you to remember how to do this. Now, you know your spatial angles, or I hope you do know your spatial angles well. If you don't, then go and revise your spatial angles. I think it is an important thing to do. Okay, I'm going to take you what the spatial angles are, and then I'm going to show you how we can do this. So in this case, remember pi over 6, if I do the conversion, pi over 6 is equivalent to 30 degrees. Okay, pi over 4 is equivalent to 45 degrees. Pi over 3 is equivalent to 60 degrees. And again, pi over 3 is equals to 60 degrees. Okay, so now I'm thinking degrees. Okay, so in your mind you'll be thinking degrees, and we will be able to solve this without a calculator. So Calculating the sine of pi over 6 will be equivalent to finding the sine of 30 degrees. Sine of 30 or the sine of pi over 6 is equals to a half. That multiplies by the tan 45. Tan 45 is 1 over the sine of 60. Sine of 60 degrees is square root 3 over 2 times, and the tan of pi over 3, or the tan of 60 degrees, which is equals to root 3. When you calculate that, that's going to give you a half over root 3 times root 3 using surds. That is going to be equals to 3 over 2. And remember, I've got a division of fraction here, which I will tip and times, so this is a half times 2 over 3, and that is equals to 1 over 3. And that is the simplification of this expression. You can type that in your calculator and double check that the value is correct. Okay, but we're not going to go into this. After the break, I'm going to show you how to do length of an arc, or how to use the applications of radian measure in order to solve problems in trigonometry at higher level mathematics. It is a formula, or there are formulas that I'm going to show you that are a lot simpler than the ones that you've learned over the last few years when it comes to calculating circumference of a circle, etc. It really is a lot simpler, so that's coming up after the break. Okay, grade 11s, I'm back. We're going to now go and look at the applications of radian measure. So I'm going to start by talking about the length of an arc. Okay, the basic formula to calculate the length of an arc is length is equals to r times theta. Okay, in this case, r is the radius of a circle that we're talking about. Theta is the angle given in radian measure. Okay, so that will be, if I had a circle, and let's just say I've got a circle here. Okay, that is my angle theta, the angle at the center of a circle, right? The length of a circumference of a circle, the length of the arc, is the length of this portion of the arc over here, okay? And obviously the radius of a circle. How can we prove this formula? So let's first start by using ratios. Obviously, it will be perhaps the easiest way for me to prove using ratios. So what I'm going to do is I'm going to say, so the ratio between the arc length, okay, in other words, the ratio between L and the whole circumference of a circle, okay, is the same as the ratio that I will find between the angle theta, and the whole revolution, 360 degrees, or 2 pi. Yes? So let's just say 2 pi. Okay? So the arc length is L. The circumference of a circle is 2 pi r. Okay? And on the other side, I've got the angle theta is 2 pi, which is a full revolution. When you look at this and you do the cross multiplication here, okay, you can then say that the only thing that I actually need for this denominator to be the same as that is to multiply both sides by r. And if I do that, if I multiply both sides by r, I will end up with L over 2 pi r equals to r theta, or theta r, okay, over 2 pi r. I obtain that by multiplying r on both sides, which is basically expanding my fractions. Because my denominators are the same, I can therefore conclude that L is equals to r times theta with the angle given in radians. And that's the proof of the length of an arc as a formula. You don't have to know the proof, you just have to know how to apply that formula in order to solve mathematical problems. It's basically the applications that we are interested in, not the formula itself. This will be area of a sector. In this case, area of a sector being the whole wedge of the pie, if you want to look, the piece of the pizza, whatever, whichever way you want to look at it. Now, how do we find the area of a sector? The area of a sector is calculated using the formula area equals to a half of r squared theta. Okay, the reason to find, or we could prove that area very simply. I'm not really going to spend time trying to do the proof of the area of a sector. Again, just as I said with the length of an arc, you will not need to know the proof. You will only need to know the application to be able to calculate the area of a sector. A couple of examples coming up, and with that we're going to finish our lesson for today.